Today we'll create a 3D printed structure to protect an egg from a compressive load using NX topology optimization. The goal is to create a part that is strong and lightweight. The shape that will result from NX topology optimization will need to be 3D printed. All designs need to have the same number of feet as well as consistent dimensions for the feet, egg support, and load pad. There are many parameters that can be varied to optimize the design for strength and weight. We'll go through many of them in the demonstration. We'll begin by modeling the egg and the egg support. Then we'll set up and run the topology optimization to create the structure to protect the egg. Then we'll modify some of the parameters to see the effect on the structure's performance. Once we have an optimized design, we'll export the files to be 3D printed. Before we get started, we'll need to get the dimensions of our egg. Once we have that, we're ready to fire up NX and create a new part file. Here we'll use the modeling template. We'll create an inch part file, and we'll give it a name. Now, before we get started, to make the user interface consistent, we'll go into Roles. We'll select under Content, Roles Advanced, and that will expand the number of functions that are available on the ribbons and in our menus. Next, we're ready to go to Expressions. You can get there using the Control-E hotkey as well. And we'll create expressions for our major and minor diameter. And here I'm hitting the Tab key to go from the dimension to inputting the value. Next we'll create a sketch. We'll do that on our front plane. And here you can zoom in using the scroll wheel on the middle mouse button. And then we'll sketch a rectangle that's roughly 2 inches tall by 3/4 of an inch wide. But before I do that, let's talk a little bit about the quick pick. If you hesitate on something before you pick it and get 3 dots, you'll get something called the quick pick menu, which you can go up to and select exactly what you want. Now we'll create our rectangle, about 2 inches tall by 3/4 of an inch wide. And we don't have to be exact because we're going to put in some dimensions. And to do that, we'll just pick on the curve and then double click on the dimension. Then we can type in equals major diameter. Then we'll hit the middle mouse button to OK that. Then double click on our next dimension. This will be our minor diameter divided by 2. And middle mouse button to OK that. Then we can finish the sketch. And we'll use that as a guide for creating our bridge curves. Now when we go into the bridge curve command, you'll see that there's already 4 entities selected. That's because our sketch was still selected. Here I'm going to mouse button 1 in an empty area of the graphic screen to deselect all. And then I'm going to select my horizontal curve on the left end of it in order to specify the tangency and the location for the start of my bridge curve. Next we'll go into the connectivity. And you can see our continuity is tangent, but we want to reverse the direction so that we're going inside of our rectangle. So we'll do that for both the start and end. And then we'll go into shape control. If that's not expanded, you can go ahead and expand it. And adjust the start and end shape so that our minor diameter is roughly achieved. Now some eggs may have a bias towards one end of the egg or the other, and we can model that, but it may be problematic when positioning our egg in the egg support. So we'll keep it symmetric. Now we're ready to revolve our bridge curve into our egg. Here I'm going to select a single curve. We'll select our bridge curve, then we'll define our vector for our axis, which will be the z-axis, and a point to revolve about. And this will be our 0, 0, 0 origin location. Okay, so there's our egg. Now, in case we want to model the egg on its side and still have it resting on the floor, we'll go ahead and create another egg. Now, we could simply move this egg, but moving it and getting it right in the middle may be a little bit more difficult than just creating another sketch. So here we'll create another rectangle, roughly 2 inches by 3/4 of an inch, and in the same fashion put in our major and minor diameters. Here we'll say no to scale the sketch if you get that question. Middle mouse button to OK that, and single click on the curve and then double click on the dimension, and then we'll put in our minor diameter divided by 2. Now this isn't quite centered, so let's put in one more dimension to make sure that it's centered. And this will be our major diameter divided by 2. Alright, and hit the enter key and then middle mouse button 2 to OK. Next we'll put in our bridge curve, but before we do that, let's go ahead and turn off the other egg that's on its end. For our bridge curve now, we'll select our vertical lines on the top end. And then reverse the direction for the start and the end, and we'll leave the bias the same. Alright, now we're ready to revolve. Again, we're just selecting a single curve here. Our axis this time will be the x-axis, and for the point to revolve about, we'll select the end of our horizontal line on the top. Alright, so that looks good. There's our egg on its side at the origin. Next we'll model our egg support. To do that, we'll create a cylinder that will be 1 inch in diameter and 1/2 inch high. So that diameter can't be modified, and our origin also can't be modified. This is going to be 2/10 of an inch below the egg. Alright, so that 1/2 of an inch is taking it up into the egg. You can see that they intersect each other. If we go to an unshaded view and then go to the display ribbon and change our hidden edges to solid so that we can see them, you can see our cylinder is intersecting our egg. And what we'd like to do is subtract the egg from our egg support. And this will provide the correct contour to support the egg. So here our target will be our cylinder, our tool will be our egg, but we'd like to keep our egg. We don't want it to be consumed by the subtract operation. So we'll say keep tool. And now if we go unshaded, you'll see that our egg support no longer penetrates the egg. Next, we'll go ahead and split the egg in half. To do that, we'll use a datum plane added distance from our origin, and here we can select the datum plane on the XY plane, and we want that to be at a distance of our minor diameter over 2. Alright, so now you can see the egg is split. Next we want to offset only one of these faces. So let's select single face there. And this will be the tolerance that we'll have around our egg. And this is something that you can vary. I'll set it to 1/10 of an inch to get started with, and you can edit it by editing our offset surface feature. And we'll see how to do that in a little bit later in the video. Next we'll go ahead and extrude the edges of our offset surface. And here we have 2 of them. So I'll select those 2 curves, and we want to extrude that downwards. So I'll reverse the direction from 0 to 1.5 inches is good. Alright, so now we have a solid and a sheet body that define our keep out zone, or our tolerance around our egg that we don't want our structure in. Next we'll combine the sheet body and the solid into a single solid body using the patch command. And if you don't know where that is in the user interface, you can type it in the search in the top right. And now you can see we have a single solid body. And there you can see our egg still inside of that solid body. Alright, so next we'll create our design space. And we'll begin by creating expressions that define the size of our design space. We're going to create a block that will have an x dimension of 4, y dimension of 4, and a z dimension of 2. So I've created expressions ds, x, y, and z for each of those. Then on the home ribbon we can create a block, and we can type in those dimensions, dsx, dsy, and dsz, for our length, width, and height. Now for our origin point, because we want the block to be centered about our egg, I'm going to select an x origin of minus dsx over 2 and a y origin of minus dsy over 2. And we want it to be right on the z-plane, so I'll leave that at 0. Alright, so there's our block. That's our design space. And so that we can see what's going on inside of it a little bit better, we'll edit the display to make it translucent. Alright, so now to define our keep out zone, we'll subtract that patched body. We don't need to keep the tool. So now you can see we have our keep out zone around our egg. Alright, so here we'll turn off the bridge curve and the sketch that we use to define and create our egg. So we're just looking at our solid bodies now. And now we're ready to define the feet for our structure. And we'll do that creating a cylinder, diameter of 0.3, height of 0.2. Those values can't be changed. Those need to be that size for the competition. And then we'll define where we want those feet. And this can be anywhere on the face of our design space. So here we're going to use the point on face. And if you want that to be right in the middle, you can type in a value of 0, so that way it's along the x-axis. And we'll create our first foot. All right, that looks good. Now we've got 2 more feet to make. Create cylinders the same size, same vector, minus ZC. This time we'll specify a point on face using the point on face in the specified point. It's a little bit quicker this way. And we want to make sure that we're selecting points so that the feet stay completely on the face. And then we're ready to unite the feet with our design space. All right, so that's all just one solid body now. All right, now lastly we'll create our load pad. And the size of our load pad needs to be 1 inch in diameter and 2/10 of an inch in height. And we want that to be in the positive ZC direction. And here we can put that point on face, but we want it right in the middle of the face. So if we select on the face, here we can see that's not quite right in the middle of it. So if we go into the point dialog, we can put in 50% for, or 0.5 for our U and V parameter. Or we could just put in 2 inches 0, 0 for X and Y and 2 inches in the Z. But that 2 inches could be taller or shorter depending on how big we want to make our design space. And then we'll unite our load pad with our design space. Now we're ready to go into the topology optimization. And we want to create an analysis type structural linear static. We'll call it egg on side 1, and we want to maximize the stiffness. Here you can adjust the resolution, but we'll leave it in the middle. And then we'll see in the topology optimization navigator that we have a number of locations where we have insufficient or missing data. So we need to fill that out at a minimum in order to get our optimization to run. So we'll begin by defining our design space. We'll pick the body that we created earlier, and you'll see it assumes it's going to make it out of steel, which is not going to be the correct material property necessarily for us. We could go into the library and select one, but instead, most likely you'll need to create your own material. So here we'll create an isotropic material. We'll change the view to all properties. We'll give it a name of ABS, 3DP for 3D printing. Here we'll give it a mass density. And we can put it in whatever units you're comfortable, or whatever units you have it in. So that way you don't need to convert to common units. Same thing with Young's modulus. We'll also need to put in Poisson's ratio, as well as 2 strength values. One for the yield strength, and we can put that in whatever units we want, and then lastly our ultimate strength. So we'll need those properties in order for our topology optimization to run. So we'll say OK, create the material, and OK to apply it to our design space. So here you can see it's ABS 3DP. All right, next we'll go into our design space. We don't need to define a construction body, but for this analysis we do. This is one of the rules we'll need to adhere to. We want to ensure that we don't optimize any part of the load pad or the feet. So to do that, we'll make construction bodies using by face and thicken offset of 0.2 of an inch. We also want transition blends to be none. So next we'll create construction bodies for the feet. We'll leave the thicken offset at 0.2. Here I can use the middle mouse button to apply, or we can select OK in the dialog. All right, next we'll put in an optimization constraint. Here we want a mass target, and we'll begin at 10% of our current design space, which will be 1/10 of a pound. And this is one of the things that we can modify to optimize our design. All right, next we'll create an analysis constraint. Here we'll allow the feet to be able to slide but stay in plane. So now that I've selected one of the faces of the feet, you can see it's defined the plane, but we want to select more faces. So I'll click in the select face in the analysis constraint dialog, and we'll apply that because we have another constraint that we want to apply as well, which is a linear slider. And here we want to select the cylindrical face of the load pad, and here I've incorrectly selected the top face. We'll be able to fix that in just a moment, but we want to specify the vector being in the Z or minus ZC direction. All right, and lastly we'll specify a load on our load pad by vector in the minus ZC direction of 1 pound. And evenly over the face. So now it appears as though we're ready to run our optimization. So let's go ahead and run it, and we'll see we get an error saying that the constrained face is used for an analysis load in the same subcase already. So it's picked up an error in our definition. So let's go ahead and fix it. We don't want our constraint on that top face, so let's edit it. We can right click on it or double click on it. So here I'm holding down the shift key to deselect the top face of the pad, and then mouse button 1 to select the cylindrical face, and it's remembered the correct vector. Our thicken offset will be 0. Now let's go ahead and try to optimize again. And here I'll be pausing the video because it takes several minutes to run through the optimization. You can see it's an iterative process. Here it's still running. While it's running, what we'll do is we'll create a spreadsheet. I recommend you create one in order to track your results. So here are some of the parameters that we want to track is the design weight, the displacement result, the stress result, our load that we're applying, which is going to be 1 pound, our yield stress, which was 5,800 psi. Then we can calculate our yield load and our yield displacement based on our unit load. And also we can calculate our strength to weight ratio. So here our first run was egg on side 1. So we'll make that our column B. And we put in weight target of 1/10 of a pound. We'll see if we hit that. We'll get the displacement and stress from our results. We put in a load of 1 pound. We know our yield stress is 5,800 psi. And our yield load can be calculated based on our applied load multiplied by our yield stress divided by our observed stress. And then in the same fashion, we can get our yield displacement by multiplying our yield load by our displacement. Then lastly, we can calculate our strength to weight ratio being our yield load divided by our weight. All right, so let's see if it's done. And here we can see it says that it's done under finalizing results. It took about 6 minutes. So we can close that and see what our shape looks like. All right, so that looks sort of like a tripod. Next, we'll show results. We'll start by looking at displacement. And here we can see that displacement is 3.94 e to the minus 5. We can put that into our displacement. We can also take a look at our result report to see exactly what the weight is of our structure. So it's 0.101, so pretty close to 0.1. Next, let's take a look at our stress result. We'll go to Result Settings, go to Stress. Here you can look at VM or worst principle. They should be fairly similar. All right, so here you can see our max is on our foot. There's also a fairly high stress along the bottom there, around the cutout for our egg keep out zone. So this is 7.2 psi. We'll put that in. And then we can see what our yield load is. So that will take a little over 800 pounds before it will yield our structure. And at that load, it will be deflecting less than 1/10 of an inch, which is our keep out zone for our egg protector. And also here you can see our strength to weight ratio. It's about 7,900. All right, so I recommend that you make one change at a time. And a good one to change is our mass target. But before I do that, let's go ahead and clone our study so that way we can keep our original results if we want to refer back to them. And then we can edit whatever we want in our second study. So here, let's make this 0.07. So we'll make it a little bit lighter. And we would expect that the displacement and the stress would go up if the structure gets lighter. But which happens faster? Will we see the yield load go down faster than the weight, or vice versa? And this will affect our strength to weight ratio. So here I'm pausing the video again. You can see after about another 6 minutes it's done, and we've got our updated results. So now we can say show results and go into result settings. You can see this is our egg on side 1. We can do a study comparison between egg on side 1 and egg on side 2. And you can see the one on the left It's a little bit smaller, a little bit lighter, a little bit higher displacement as we expect. So let's bring up our spreadsheet and we'll put in our egg on side 2. So here we can put in our displacement. Next we can look at our stress results. And you can see our max stress has gone up as well, as we expect. And then for our load and everything below that is going to be the same in terms of a formula. But let's go to our results report where we can get an exact value for our weight, which was 0.0707. And then we can copy and paste. And there you can see that our yield load has gone down. Our yield displacement is still less than that 1/10 of an inch of our keep out zone that we defined from our offset surface. But you can see that our strength to weight ratio has gone up. So this design is better from a strength to weight perspective. All right, next we'll look at how we can modify many of the parameters to optimize our design. So we'll begin by cloning our study. And for this one, I'm thinking about putting the egg on its end, so we'll call it egg on end. Then we'll finish to exit the topology optimization environment, and we'll make some changes. So here we'll make a change to the size of the egg. We'll go into the expressions editor, and so we can see the egg. We'll make some changes to the major and minor diameter. And you'll notice when we say OK, not only does the egg change its size, but also the keep out zone in our design space changes. So let's go ahead and hide the block. And we'll also turn on the egg that's on its end and hide the egg that's on its side. And you can see the egg holder still reflects the egg on its side. So let's edit that subtraction operation that made it. And here for our tool, I'm going to hold down the Shift key and mouse button 1 on the egg on its side to deselect it. And then we'll mouse button 1 to select the egg on the end. And you'll see that our egg holder now will hold the egg on its end. Next we'll edit the split body that split the egg on its side. I'll hold down the Shift key, mouse button 1 to deselect the egg on its side and select the egg on its end. Then we also need to edit the plane. And here we'll edit the formula of the plane. It was the minor diameter because it was on its side, but now that it's on its end, we want it to be the major diameter divided by 2. So now our plane that splits the egg in half is at the correct location. And you can see we have some X's here next to some of the other features because it can't find some of the reference objects for selecting the face for our offset. So here I'm going to mouse button 1 in an empty location to deselect all objects, and then we'll mouse button 1 to select the egg on its end, the top half of it, to create our offset. All right, in the same fashion, you can see our extrude. Can't find those curves for that extrusion. We'll mouse button 1 to deselect all, and then we'll select the edge of our egg on the end. Here we get a question about mapping the parents, which we could do, but it's unnecessary, so I'll say no. And now you can see that all of our features are up to date. So if we turn on our block, we can see our keep out zone has updated That looks good. The block, however, may not quite be tall enough now because our egg is on its end. So let's go back to the expressions editor and change the size of the block. So we had it as 4 by 4 by 2. Let's make it 3.5 by 3.5 by 2.5. All right, and I'm hitting the Enter key after typing in the new value, and then OK. And now you can see the size of our design space has gotten larger. One of the feet, though, here you can see it's off the edge. We'd like to make sure that's on the face of the block entirely. So to edit it, what we can do is change in our selection bar to select features. Then I can double click on it, or we could edit it out of the navigator as well. And then we'll select a new point on face that's a little bit further inboard to make sure we're entirely in the design space. And we'll do the same thing for the other feet. Here we need to make sure we're standing on the specify point in the dialog so that we can specify a new point for the origin of our cylinder and say OK. Alright, so let's go back and edit our topology optimization. Here we've got our egg on end 1. You can see everything appears to be up to date and ready to solve. So we'll go ahead and hit optimize. Here I'll pause the video. You can see it's done after a little over 5 minutes. And we can see the new optimized structure based on the egg being on its end. Here you can see our mass target was hit within 1%. So here let's record our results for the egg on the end. Here we can show results. We'll go side by side with egg on end 1 to egg on side 2. So here let's put in our stress result, and we can also put in our displacement result. And then we'll copy and paste the rest of it in order to get our yield stress, yield load, yield displacement, and our strength to weight ratio. So there you can see it's quite a bit better at over 10,000, and our yield displacement is not greater than our keep out zone, which was our offset of 1/10 of an inch. So that all looks very good. Once you're happy with your design, there's one step left before we're ready to 3D print it. So here we'll finish our topology optimization, and we'll go into polygon modeling. And if you don't have a ribbon for that, you can right click in the ribbon area and turn it on, and then you can go into polygon modeling, clean up facet body. We'll select our design, we'll say create copies to edit. Then we'll go to Analysis and Repair and Analyze. And here you can see we've got a couple degenerate facets which we can repair. Alright, so now we've got a clean facet body ready to export. So we'll go into File, Export, Stereolithography, specify where we want to put the file, and give it a name. Now I'm also going to turn on Review Errors once we select the facet body. And we'll say Apply. And here you can see we've got an error, negative coordinates found. So if your 3D printer cares about the part being in positive space, we'll need to move it first. And we can do that with Edit, Move Object. Now here we'll use the quick pick. We'll hesitate until we get the 3 dots. And then we'll select mouse button 1 and select the convergent body, as well as our egg support. That way we can move both of them at the same time because we want to 3D print both. We'll say copy original, and the motion will be dynamic. So that way we can just drag the handles to get the part in positive space. So here we'll just make sure we drag it far enough to be past the y-axis in the x direction, and then far enough to be past the x-axis while we're dragging in the y direction. And then also we need to go up at least 2/10 of an inch in the z direction. Alright, so that should put everything in positive coordinates. So let's go ahead and export our STL file again. Here we'll give it a name EP_1 and no errors. Then we can do the same thing with our egg support. And we'll call that EH. Now once you're done, before you exit, let's go ahead and make sure we've saved everything. Alright, so that is how to create a structure to protect an egg from a compressive load using NX topology optimization.